Thank you for the invitation today to Manju and Paul. I'm pleased to be here. I've been a charter member for about pretty much 30 years. And I'm going to make this a sort of a balanced talk. So a lot of talks in the value you find are either sort of hand wavy, AI is going to be Terminator, or it's going to predict the stock market, or they're too mathematical. It's just too much math and it's too difficult. And when I talked to Manju and Paul, I said what we're trying to do in the bootcamp is somewhere in between, right? So it's a double click on how some of the core techniques are working, and a little bit of biology. There'll be a tiny bit of math today, but not much. But the idea is to give you the tools to think for yourself. So, right, so the idea by the end of it is you should be able to converse with practitioners, people who are in the industry, people who are journalists, be able to critically evaluate when you hear something on the radio or on the New York Times that says AI people are being paid $1.5 million a year. You can think about, is that true? Could that be true? We'll come back to that later. And then think about what the future's going to be. Basically, we want to go with where the puck's going to be, not where it is now, right? So that's the thing we need to get to. So try and understand what the limitations are. I'm going to talk a bit more about neural networks, sometimes known as deep learning, and show some examples and go through a little bit of the math around there. So who am I? I've had an academic background and an entrepreneurial background. I've first worked on neural networks in 1986. So those of you who think it's only 5 or 6 years old, it's actually more like 60 years old. So I was late then. And I was lucky enough to get the Mountbatten Medal. So in the Indian crowd, we know who Mountbatten is. But that was in England for the work for applying AI to mobile phones and mobile infrastructure. So my reputation is starting companies and selling them to mobile companies. So the first one was to Motorola, which did handwriting recognition, Cellmania, which did app stores, to BlackBerry, and then more recently Vocal IQ to Apple. And I'm at Stanford these days. I'm a fellow at Stanford University, and I teach a course like this. And that tries to balance biology, mathematics, computer science, and then I'm part of a project where we talk about the boundaries of humanity. So where does the intersection between machines, humans, and animals, what's different between intelligence, in those disciplines? I was going backwards this way. Click the right button. So what are my contributions? I worked on speech recognition, some of the earliest speech recognition phones, earliest handwriting recognition, and this handwriting recognition is cursive, where the letters are joined up. Some of the first mobile app stores, this is like in 1999. And so the idea is, how do you build intelligence into a device? So one way you can use machine learning, another way you can do crowdsourcing applications. But where did I get my inspiration from? So I got my inspiration from the movies. So maybe I should just open it. What are our favorite AI movies? Anyone got a favorite AI movie before I cold call on you? 2001: Space Odyssey, 50th anniversary. And what's the device there? The machine for the younger people who haven't seen that. HAL, which is, those of you know, it's one letter above IBM, so actually below IBM. And what about Adar? You work for HTC. What AI movies can you think of more recently?
I think one that was released last month, Ready Player One.
Ready Player One. Yeah. Anyone see Ready Player One? No, it's pretty interesting.
What about Star Wars, R2-D2?
R2-D2 Star Wars. It's Ex Machina, her. Well, anyway, for me, for people of my generation, it was Star Trek, right? And so it's computers and androids. And what's kind of interesting is that a lot of the things in Star Trek have actually happened, right? They've actually happened, because you've got the communicator, you've got tablet computers, you've got devices that sense things. What hasn't quite happened yet is this Android. We haven't got data yet. We haven't got data talking to himself. And so I'm often talking to young people, and why I became an engineer is because of watching lots and lots of episodes of Star Trek, and they said, yeah. And then I suddenly realized they're thinking about the movie, and I'm thinking about the TV series. So the first speech recognition system that I built was in my undergraduate degree in 1984. And this was to be able to recognize voice dialing. So you could say 650-281, but in connected fashion again. In those days, the main research, R&D, you had to have a pause in between each word. So we don't think about that now, but some of the difficulties that we think about today, we won't be thinking about today in the future. And sometimes people think that, what is artificial intelligence? Well, once you've actually implemented it, it's actually not, it's not artificial intelligence anymore, it's just a feature in a computer. But we were looking at like 8-bit computers, 8 kilobytes of RAM to implement this kind of thing. So the amount of computing power we have today is compared to 1993, I haven't done the calculation from 84, but 1993 is like 65,000 times more processing power and a similar improvement in memory. So got speech recognition in a laptop. At that time we could only do 64 words at a time. And even though it had a reasonable vocabulary, 4,000 words, which is like nothing today. But some of these things have been worked on for decades. And most of the things, in technology and science, we build on other things that have gone before. And that's what's going to happen going forward. Things that will come in the future will build on what's happening today. So cursive handwriting recognition. This was being able to recognize letters that are joined up. And this is, again, 1991. And there was a sort of fits and starts of mobile devices coming through in that area. And then that finally led to me getting on the cover of Fortune magazine. And what's interesting here is this title, this title and the article, you could probably reprint the exact same article today. It talks about robots, stock market prediction, speech recognition, factory automation. This is one of the things to think about is, the industry is always 5-10 years away, and people have been thinking about this, and what can happen. So what's different now? Vocal IQ, there's a company that did speech recognition for dialogue systems. So when you ask, I want to go to a restaurant in Palo Alto, it comes out with a list. I want a Chinese one, it comes out with a list. When you ask Siri, I want one with Wi-Fi, it might give you a list of routers because it thinks you're on a different topic. So what Vocal IQ did was maintain the state of the dialogue. So first of all, what is intelligence? So who can give me a stab at that? Who can say, what is intelligence? Before we get to artificial intelligence, can anyone give me an idea? Over there. What's your name, sir? Mehul, yes, off you go.
You look at the past, intelligence it's like a child, how they learn anything. So you learn from the past and then your future is better. Okay,
so it's like a child, learn from the past. Anyone else want to add to that? Want to have another go? Over here. What's your name, sir? Ron.
Come up with right answers, whatever you think right is.
Come up with right answers, whatever you think right is. One more go. Anyone else? Over here. Your name, sir? Ranjit.
Ask good questions.
Ask good questions. Okay. 30 years ago, the Wall Street Journal asked 100 researchers, 100 academics, what is intelligence? And we'll come back to this definition at the end. But at that time, the definition was a general mental capability, not merely book learning, reflects a broader and deeper capability for comprehending our surroundings, catching on, making sense, figuring out. So basically what it's saying is, we're not quite, it's a difficult definition, we're not quite sure what it is, but we know it when we see it, right? We know, that's basically what he's saying. Intelligence would be, today, and we'll come back to this at the end, certainly if you ask a psychologist, people talk about self-awareness, emotional knowledge, creativity, these sort of human-like elements. But what is AI today? So what's artificial intelligence? Anyone? No, that's intelligence, real intelligence. What's artificial intelligence? Anyone want to have a go at that? Where are we seeing AI in daily life? Where are we using AI right now, practically? Over there.
So based on the previous knowledge or learning,
Yes.
we're able to predict what's
Okay, based on the previous knowledge or learning, we're able to predict what's happening. So I'm thinking more about applications. Where are we using it? Just today, you came to work. Google Home, Nest.
Machines trying to do human behavior.
Machines trying to do human behavior. Speech, vision. What's over there? Self-drive. Actually, can you actually buy one? I don't think I can buy one. Maybe you can buy half of one, right? Maybe Tesla. Pandora tells you what you want to listen to, right? Traffic. Right, so there's lots of different things. These are things that are we are actually using AI in daily life. They tend to be practical things. But when people use the terminology of AI, people get a lot confused in what these different things mean. And so I'd just like to go through, so you just know the technical definitions of what happens. So first of all, we've got GOFI, good old-fashioned artificial intelligence. And that's basically the AI techniques that were used in the 70s, maybe early 80s, which, I'll just come back to a second, early 80s, which is basically writing down rules, if then, or the special languages were developed, Lisp, on how to solve a problem. So if you want to diagnose a person, has this person got appendicitis? Has he got a pain here? Has he got a pain there? A little rebound test. You go through a list, if then it comes down with a list. Is this a human or is this a dog? Is it a dog or a cat? What are the elements of the data? And someone will basically, you sit down a guru and you extract from his head why he thinks this patient should be diagnosed this versus that. So it's what we call some rule-based system. Sometimes we call it symbolic-based system, symbolic processing, and that's good old-fashioned artificial intelligence. So machine learning is the next step. So machine learning is learning from data, learning statistics, and there's lots of techniques, random forest, logistic regression, linear regression, hidden Markov models, support vector machines, and we're going to do a double click here on neural networks in this talk. So what was your question?
I just want to check if you'll be sharing these slides.
Oh, right, yeah, sure. Yeah, I'm not sure how they get to them, but yeah.
We have your email ID, so we'll make sure it gets you. Thanks.
Okay, so next thing you've got artificial intelligence. I'm saying basically artificial intelligence, the actual definition is human-like functions, right? So is it human? Does it have guilt? Can it love? Can it be creative? And most of the things we see in industry today is actually not AI, right? It's more not by the technical definition. Even at university, even my own class, even the classes, we say, oh, well, the first thing we say, well, actually we're doing machine learning, but the class is entitled AI, and it's very vertical solutions. And you've got two types of AI, strong AI and weak AI and AGI, generalized artificial intelligence, which is basically people have modified this terminology to say weak AI is kind of like machine learning. It's sort of solving a vertical problem, solving speech recognition, solving stock market prediction. But strong AI is like real human intelligence, right? So we're actually creative, creating art, creating stories, trying to actually have a conversation like you and I are having today. So these are the technical definitions, but what you'll find is in the press, actually not just the popular press, not just the mainstream press, but also the academic press, all these terms are used interchangeably, right? So if you get in a debate saying someone says to you, oh, well, that's not AI, that's machine learning, or that's not machine learning, don't get in the rat hole. It doesn't really matter. It doesn't really matter. Maybe some of the marketing people here might want to differ from that, but from a technical point of view, it doesn't matter. The higher order bit is what problem you're trying to solve. And clearly, yeah, if you're trying to make a human-like thing, it's a different level of problem. Symbolic processing, you need an expert. The thing is, sometimes people have asked me, is there a role for rule-based systems versus data-driven systems where you just collect the data? And you've got to think that I think right now people are always talking about statistical systems, collecting parameters of the data sets and learn from the data instead of just writing down the rule. I think the important thing is to think about what problem you're trying to solve. Some problems don't lend themselves as well to the data problem. So the example I usually give is like, if you want a machine that files your taxes, we actually know what the rules are, right? Somebody's actually written them, right? So you don't, maybe that's not such a good example where you want to collect lots and lots of people's tax filings and see what numbers to put in the form, because that's more of a rule-based problem. There are other time-varying problems that people will talk about. Are you just looking at a picture, a static picture, or is it a video where things are moving accordingly? And the thing to think about, like these are sort of things you'll see in the literature, sort of statistical techniques, mathematical techniques. It's important not to get them confused with platforms. Right, so sometimes people think TensorFlow, and Andrew's going to tell us a lot more about TensorFlow later on, is actually an algorithm. It's not an algorithm, it's a platform that implements some of these algorithms. And most of the big manufacturers have various platforms that are out there, and here's a few that are there. We've got TensorFlow, is quite popular, digits from NVIDIA. H2O is an open source system. So some of them are open source, some of them you have to actually buy. So, next type of learning is supervised learning versus unsupervised learning, right? So, supervised learning, which is most of the problems you see today, is where you have a data set and the data is labeled, right? So the data is labeled. You take the handwritten character example. You take lots of handwritten characters, have them labeled. So typically the data set is labeled manually. Often a lot of the techniques we need a lot of data, and so there are ways to actually increase the amounts of data. So maybe we've got this set of handwriting characters and we want more examples of 5. Well, we can mathematically just perturb the data and turn it upside down, turn it sideways to create more examples, as opposed to actually having someone to write the number 5 again. And the workflow is basically taking data, turning it into features. We'll talk about a little bit about feature wrangling in a minute. Training a model, and once you have a model, that's your model set. And when you get a new character that you want to predict, what is this character? Is it a 5 or a 6? You try and find the closest model, or have the model predict that number. So supervised learning is where you have labeled data. Now, unsupervised learning is where you don't have any labeled data. The data is not labeled. And so typically you are clustering the data. So some of you, if you're in the marketing world, we do this as a human trait. We try and find market segments, and we say, okay, that market segment is old people, that market segment is young people. But we try and do that mathematically. So you find lots of labeled data, and we search for patterns, and you can use quantization techniques and clustering techniques. And here's an sort of example of sort of movies. And you take sort of parameters of movies, of who are the stars in the movies, who are the stars in the TV show, where was it played, what country was it played, what channel was it played in, what are the other characters, what are the other actors. And you can find that in this particular one, it sort of clusters, and some of them labels them as some of the British comedians, some of them are TV shows, some of the classic comedians, some of them are movies, and it's a clustering technique. And so going back to the problem is trying to find the right tool for the right job, right? So sometimes one wants to sort of jump into a machine learning type technique, and when you could just simply write the rule. Sometimes, like stock market prediction, you could have a debate, right? Maybe you do get a financial analyst who's got built up a set of rules in his head and is pretty good at picking stocks. I think Warren Buffett doesn't probably use many machine learning, but he's got sort of built up in his head a pattern of what stocks would be useful to buy. Where statistical techniques work, machine learning works, it's typically problems where we actually don't know how to solve the problem very easily. Speech recognition, we still haven't solved that problem, to Star Trek levels at least. Machine vision, we're getting pretty good at that. And a big difference from like 30 years ago to today is this field is a lot more interdisciplinary. So it used to be in the field of computer science. It was just computer scientists and mathematicians that worked on this. And today there's a lot more groups. They're either trying to contribute, neuroscientists, biologists, physicists, engineers, or they're trying to actually use these techniques in their own problems. And that's a big difference. And what's kind of interesting, if you actually go back, back to the 50s, a lot of this work was actually driven by neuroscientists, not computer scientists. We'll go into that in a second. And AI has gone through a lot of summers and winters. Usually people date it back to a conference at Dartmouth, where even at that time people said the target, it was in 1956, that's 1956, the target was, okay, we will have a machine that can be conscious and act like a human being within 5 years. This is 1956. And they got lots of money to do a lot of research, but then that sort of dried up. In the early 60s, the people started working on neural networks, but they thought they could only solve simple problems. So Marvin Minsky at MIT wrote a famous paper that said, well, we can only solve simple problems. We'll talk about linear problems in a minute. In the 70s, late 80s, there was a lot of work on expert systems. And then the first boom in neural networks was in the late 80s. That's when I started getting involved in it. And popularized by David Rumelhart over at Stanford University. Again, he was a psychologist. I can remember coming to America for that, and I wrote him a letter saying, I've got this fancy fellowship to come to America, and can I spend a year in your lab? And he said, yeah, sure. I know you're a professor at Cambridge. And I didn't know, because all his papers said Department of Computer Science and Psychology. And so I just assumed I'd be in the computer science department. I show up and then I'm in the psychology department. And I know nothing about psychology. But it turns out it was great. He'd collected physicists and linguists and mathematicians to work on this problem. Over there, you have a question.
So why do you think these cycles happen? Is it just because the human was limiting themselves, or computing power? Why do you...
Yeah, I think it's a broader question on science. Science, on how science and maybe probably science and related to industries and technologies, I think as well, on how products get made, get forgotten about, and then remade when the time is right. Einstein says basically, he's got a famous quote, it says basically progress happens when people die. Right, he got his Nobel Prize. He said, well, I got mine because everyone else died, and so finally they recognized my work. And so we have these cycles. Again, we've got since in the last 10 years or so, we've had more computing power and more memory available, and people realized that I think NVIDIA started handing out C compilers for their GPU, and then scientists said, well, why don't I just run our algorithms on the GPU, and it's like 50 times faster, so you can get like much more experiments done than you can done before. And going back to your question about the classic technology emerging life cycle, this is a classic, they call it the hype cycle, I guess, from Gartner, where you can take any technology and plot it on this curve. And typically, we've got like things like smart dust, which is just like people are just thinking about now, really early, that 10, 15 years, quantum computing. Actually, I think quantum computing is probably 20, 30 years away, but quite early. And then you get this hype where people think, okay, it's the bee's knees, best thing since sliced bread. So, deep learning, machine learning, we're in that phase there. Then all of a sudden people say, well, actually, it's not as useful as we thought. Like augmented reality, I remember people talking about that 10 years ago, maybe 15 years ago, being very excited about it. And then all of a sudden people said, well, I can't find many applications. But then things get, well, actually it is kind of useful. So VR is kind of like that. People saying, we can actually find real applications for it now. But people have to go through this curve. Now, the thing in AI, the school of thought, it actually doesn't happen like that. We don't actually go through this curve. We have this boom-bust cycles. And the important thing is, as practitioners and thinking about our careers, yes, certainly we are in a period where everybody is interested in the field of artificial intelligence. But at some point, there's a debate about, is this just a transitional technology? Is this just like, it could be like electricity. That's the phrase a lot of people say. It's like it's a new electricity. Well, new electricity means it's commoditized. It's just a tool in your toolkit. 10 years ago, 10 years from now, it would just be a tool. It'd be like internet, right? Internet in the late 90s. It was very, very high profile. Now no one even thinks about it. You don't really have conferences on sort of like internet companies like we had before. And so that, I think, is something to sort of just put in the back of your mind. The main part of this workshop is that you have the tools for yourself. So by the end of the day, you can have a debate with me, and you could be just as right as me, right? You can think about it for yourself. And talking about hype, in this field, we get a lot of outlandish examples. This is Sophia. Has anyone seen Sophia on TV? Sophia, yes, TV. This is a robot. It's given citizenship in Saudi Arabia, and it's quite a nice demonstration. I don't think we have time to go to the YouTube here, but most people feel it, and the inventors even say it is a CAN demonstration. It's not actually interacting with you. This is a robot. It's a lady robot. It's interacting. It's been on the Jimmy Kimmel show and telling little jokes. But even the inventors will say that it is actually pre-programmed. It's not a self-aware demonstration. But for the average person who's looking at it, they actually think it's real. It's actually self-creating its responses. So again, when you're sort of listening to articles, you sort of have to double-click, and say, well, okay, how's that working? Based on what we know, and what could be pre-programmed versus what's interaction. And this goes back to the strong and weak AI part. Most of the things we look at are weak AI. Most of them, there's nothing wrong with that, but they're narrow embodiments of the implementation. Right, neural networks. Actually, before I go into that, what is the background of our audience here? So how many people have non-science backgrounds or non-engineering backgrounds? Okay, a few people. And how many people have actually done some machine learning already? It's about half. Great. And how many people work for AI companies? So what kind of company do you work for?
We are a machine learning company to create the content.
To create the content, right, okay. And how many people work for an AI company but not in an AI function? like HR or something like that, or legal, law, or sales. Great. Okay. Right, so I'm going to sort of double click on neural networks. So some of this might be familiar to you and some of it not. Some of you might be using it as a black box. Some of you might be more knowledgeable about it. And why are we using neural networks now? And what is the difference between neural networks and deep learning? So these techniques have been winning a lot of data science competitions. Why is that? Today we have a lot more data, and today we have a lot more computing power. And a lot of the highlights in the press, I think, we don't really see many articles on support vector machines in the New York Times, or even hidden Markov models in the New York Times, but we see lots of articles about neural networks. Why is that? Because people are, the techniques are inspired by brain-like processes, how neuroscience works. I'm trying to get across a little bit about that inspiration. And it used to be the case, neuroscientists and computer science wouldn't even be on the same stage together. Now it tends to be a bit more cooperative on what can we learn from the brain. And we also have better tweaks on the training algorithms, more sophisticated architectures now to solve interesting problems. And as I said, this basically was popularized sort of in the mid-80s by David Rumelhart at Stanford University. He wrote some classic books on how the backpropagation algorithm works. And I'm trying to give you a bit of intuition on how that works. And he was a psychologist. And really interesting examples are, I think Lalit might be able to help me. I'll show a demonstration here. And this is the deep mind brickbreaker example. So this is an interest playing an Atari game called Breakout. And the interesting thing to know is all it's seeing is the bitmap and the score. And it's not told any rules on even how to play. All it knows is the bitmap, the score, and it can move the bat sideways, left and right. That's all it knows. And at the beginning, it's not too bad. It's sort of playing it like any of us might play it. And the objective is to break through this wall. And it's having a go. After a couple of hours, it's a lot better. It's a lot better. Right, yeah, so it's pretty good now. It's a bit like after we've played it for a couple of hours, it'll probably be as it's getting faster. Yeah, it's probably better than us at this point. And then after a few hours, it actually figured out a rule that most humans haven't figured out of how to actually play this to get a really good score. And I'll leave it to show you before there you go. It's tunneled through. It's tunneled through to get the answer. So these are little demonstrations that are sort of give you the idea of what's going on. And DeepMind, they got bought by 500 million after that demonstration. Probably not just for that, but it's a they use something called reinforcement learning, and you're getting examples where some of the machines are better than humans, right? So the example is how Google made a implementation that played Go. Actually, does anyone actually play Go? Who knows how to play Go? Does anyone know? No one knows how to play. I don't play Go either. So it's more complicated than chess, but it's kind of interesting. Again, think for yourself. What is Go anyway? First of all, why is that an easy problem or not? I like to think for yourself and double click a bit, but I'll take it on face value that it's more difficult than chess, more complicated, and the poor old human lost to the machine. And it's interesting, it started from blank. It didn't have actually any data. It created the data itself by playing itself. And the order of magnitude of processing power, and so AlphaGo 0 is the newer version, versus AlphaGo. It might sound it's supposed to be the opposite. But we're talking about the first implementation, a couple of thousand servers. Now we're in a few dozen servers kind of thing. And training always takes more than tests. So this is a fundamental lesson. A lot of people don't realize this, but training always takes longer than the actual test, the playing part. Because once you have the model, it might take you a lot of data, a lot of time to process it, calculate the parameters. But once you have it, then you can implement it accordingly. So how does that compare to human? Right, so AlphaGo is running at like 10 to the 16 flops. Flops are floating points, operations per second. So 10 to the 16 flops. So what does a human do? We run at 0.01 flops, right? So you can work that out yourself. You can say, well, how long is it going to take me to add up these 7-digit floating point numbers in my head? Because we're a bit brighter here at TiE, probably less than 100 seconds, but order of magnitude, 100 seconds. We have about 87 billion neurons. Each neuron's connected to a few thousand other neurons. And just a sort of order of magnitude, your smartphone is like 10 to 11, 10 to 12 flops. So, people sometimes think that so the smartphone is only like a 10 to the 3 difference. So if you use Moore's law, that's 7 to 10 years. If you can get there, though there's a debate whether Moore's law is flattening out. And there's a school of thought that it's going to take us 10 to the 18 flops, which is only 1,000 chips, right? It's not like a million. So, but we'll go into what that means. What does that mean? It goes back to, can you actually do intelligence in a device? Good, we've got time. All right. So there's different types of neural networks, and Manju's going to go through other types, LSTMs, recurrent neural networks, convolutional neural networks. I'm just going to go through a very simple neural network. We'll do some hands-on, very simple hands-on. But if we go back to the brain first, the brain's got 87 billion neurons in our head, in our brain. And the neuron is the basic cell in the brain. And the cell takes electrical impulses, and sends it on to, it takes electrical impulses from other neurons through these dendrites, and then sends it on to other neurons. And there are lots and lots of neurons in your brain, and different animals have different numbers of neurons, so it can be just a few hundred from a small creature, creepy crawly. Dolphin, 38 billion neurons. And so in computer science, we've got this thing called the perceptron, which we try and create a very simplified mathematical model of what a neuron is. So we take inputs. So what are inputs? Inputs could be stock market values, could be pixel values, it could be sound amplitudes. We multiply each input by a weight, add them up, and then push them through a function. And this was actually suggested in 1958 by Rosenblatt, who's actually a neuroscientist, not a computer scientist. And in those days, he had basically a whole room to basically implement this. I did see a picture of that once. And this was reported in the New York Times, so we're still getting articles like this, say that the Navy revealed an embryo of an electronic computer that expects to be able to walk, talk, see, write, reproduce itself, and be conscious of its existence within 5 years. Right. But what's interesting, this is like science, I think the question over there now, why are these cycles? I mean, the root technique can be traced back to 1958. So we connect all these neurons together, and so what kind of problems can we solve? So Boolean logic, George Boole was in the mid-1800s, a mathematician in County Cork in Ireland. unfortunately, he caught his death of cold, and his wife was a homeopath and wrapped him in wet blankets, and he died 10 days later. But he came up with this concept known as Boolean logic, which I know a lot of us have done in our electrical engineering classes or mathematics classes, but it might have been 10, 20, 30 years ago. So just as a reminder, you've got AND gates and OR gates. So AND is if both things happen at the same time you send an output. So the example I've given here is, like, if I eat my vegetables and I'm hungry, then I can have ice cream, right? So think about the traffic lights. In certain areas, you want if both happen, then it will let go. Otherwise it won't let you go. Or is you just need one of two things to happen to send a positive output. So if it's the weekend, or I've got vacation, then I go to the park. Right. So this is what's Boolean, and we call this basically. This is what's called a linear problem. We can actually put this in a coordinate space, and we can actually just draw a straight line between the problems. But we have something called XOR, which basically says, the example here is only if I've got one of the things going do I spit it out, but if I've got both, then I have to put a negative output out. And the example here is, if I eat tacos or pizza for breakfast, then I'll be happy. But if I don't have one of those, I'll be sad. But if I have more than one, I'll be sick, right? So this is sort of an XOR problem, and this turns out you actually can't draw a straight line between this. Probably put this in the coordinate space, you actually can't draw a straight line between these things. You actually need two straight lines. And so they call that a nonlinear problem. And a lot of problems are nonlinear. So we get patterns, and we actually cannot draw patterns can't draw a straight line to separate the red dots and the green dots. We have to sort of do a sort of complicated pattern to separate the green dots from the red dots accordingly. And so this is what's called a nonlinear problem. And neural networks are providing this analogy to the brain. You've now seen in the mainstream press that artificial intelligence, neural network can predict a lot of different things. But you can also trick them. There's an example here. You can actually trick neural networks. There's a whole field of how you can sort of present other things, and it comes out completely the wrong answers. So going back to the neurons, so all these neurons are connected together, and how does the neuron actually work? You have electrical impulses coming in, but it doesn't send an output until you get a certain strength. When it gets to a certain strength, only then does it send an output to the next neuron. And so how do we implement that mathematically? We basically have inputs, add them up, and then stick them into a function. And the function is set up so that only, we got that one. This function is set up so that only if it's above a certain level do you send it on. And for many years you use this function here for no particular reason really. These days we use this function, which is actually simpler to implement. So if you add them up, and if it's above 0, send it on. If it's below 0, just send 0 out. And so we connect these in layers. This is gross simplification of the brain. It's nothing like how the brain works. So we connect these neurons together in layers. And we have these weights from one neuron to another neuron. Now how do we compute the weights? That's the next question. The components of the neural network are then the inputs, the architecture, the number of layers, the weights, and then the activation function of the actual input. So first of all, what are the inputs? Inputs could be, again, pixels, values, stock market values, sound values. Words, we have to turn them into numbers. You can't just send words into a system, you have to turn them into numbers first. And typically you are turning these inputs into features. And there's a big task of actually how do you actually turn these into features? And do you need to turn them into features? And you call this data wrangling. And so often when you have a big data set, there are examples that are missing, examples that are in error, examples that are duplicates. And so as a result, you have to do a lot of processing to actually put them in a normalized fashion. They may be in different databases. You know, this is an example in many industries. We've got the data, but some of it's in my HR database, some of it's in my payroll database, some of it's in my finance database, and we have to put this all in one place. And I think we have some other speakers talking more about how to do that. And there is a trend, and there's several examples where people have said, well, I don't need to turn these into features, I'll just throw the data and let the machine figure it out. Usually that takes a lot more computing power, a lot more memory, a lot more work for the machine to learn. But there's another disadvantage, is that often one of the disadvantages of neural networks, actually it has so many parameters and so many weights, it's more difficult to figure out why it's decided a certain problem. And if you haven't turned your data into features, it's even harder. Okay, so how do we compute the weights? So let's start with just something simple, just two layers. Let's say we have, this is the basic process. So the objective here is to just get you the intuition, because often you just see this thing called a neural net and you just run it and you're not sure what's going on inside. I'm going to give you just the example here. Let's take the inputs. Maybe we're trying to recognize the difference between caterpillars and ladybugs. So ladybugs are short and fat, caterpillars are long and thin. So maybe our two inputs are the length and width, right? So we take data in and and we now have to figure out what are the weights. So first of all, you just simply put weights in at random, right? We just choose these weights at random. And figure out what the numbers come out to be. And then each node, each of these circles, we put the weights, multiply the input by the weights, and put it through a function. So we're actually going to do this here, because I was told this is supposed to be a hands-on thing, so you guys are going to calculate this for me. And so to get 1.05, how do we get that? Does someone want to tell? Maybe someone knows already, can have a go and tell me how I got 1.05. Anyone have a go? Okay, I'll do the first one, 1.05. So we put these weights at random, and what we do is 1 times 0.9, right? Actually, I'll do the second one, because we've actually written it down here. 1 times 0.2, so 0.2, plus 0.5 times 0.8, so that's 0.2 plus 0.4 equals 0.6. That's the answer, 0.6. Right, so who can tell me how to get to 1.05? Anyone have a go? Over there, he's going to have a go. 0.5, where are you going? 0.5 multiplied by 0.3, yep. That's, how much is 0.5 times 1.3 is? 0.15, thank you. And then keep going, sir. Right, so plus 1 times 0.9, and that's how you get 1.05. Right, and then you stick this in a function. I need to change this to the rectified linear, it's much easier, but our sigmoidal function, we put this number up here and we get these numbers out. So this is two numbers, the final numbers are 0.74 and 0.65. That's a very good question. So initially it was thought that that's how the neuron response was based on that function, because when you go to a we're trying to get the neuron, the way it works, it doesn't just pass it on automatically. It needs to get to a certain level, right? It needs to get to a certain level before it sends it on to the next neuron. So people a lot thought this, well, a sigmoidal function is a pretty reasonable function because once it gets to a certain level, it will go there. But equally likely, good one, maybe this one or this one. And for about 30 years, we used this one. And then people said, oh, hang on a minute, let's try this one. And this one worked a lot better. So again, it's going back to the other question over there. But in science and in industry, we often just do what the other guy did. And one of the lessons here is you don't have to do what the other guy does. You can think for yourself, right? And there's lots of experiments that you could do that haven't really been done in this area. A lot of people haven't done things. Over there.
Yeah, for probabilities, you can actually derive this function from conditional probabilities and base theorem.
Yes, that's right. That's another reason. Yes.
Probably early motivation.
Yeah, that's an early motivation. Yeah, exactly. So different people, depending on what field you were in, you had different motivation. If you're a biologist, well, yeah, I've seen my neurons have this kind of area. If you're a mathematician, probability theorist, it's oh, well, obviously it's like that. But as an engineer, I just want a thing work, want the thing to work. And so these days, this is the most popular activation function. So, okay, we've done that. And so if we stick this through 3 layers, you can do the same calculations, put weights in. And what you find is you can actually do those multiplies. You can actually put them in, once you have lots and lots of layers, lots and lots of neurons, you can actually put them in matrix form and do matrix multiplication. So I won't go through matrix multiplication today, but that's one of the reasons why GPUs are very useful, right? And that's why NVIDIA's stock price has gone up 3 times in the last 18 months, because those functions are much easier to implement on a GPU than it is on a CPU. All right, so we calculate these things. Right, we calculate these things and we say, okay, if it comes out as the top one, it's a caterpillar. It comes out as the bottom one, it's a ladybug. You know, we put length and width in. But let's say we put the length and width in, and it's actually got it wrong. Right, so how do we actually update? Because these weights that we came up with at the beginning, we just came up at random. We just put those at random. And so one way to do it is basically update the weights, and update the weights in proportion to the size of the weights by the error. And so we have this technique known as backpropagation, where we work out the rates at the end, right, and then are able to figure out the error on the previous layer based on the previous weights, and keep finding the weights accordingly based on each layer. So you can find the error or the output, but how do you find the weights in the middle? And so we have this one technique is you could just try every combination of weights until you get the right answer. But that's too difficult. Even for a computer, it's too difficult. It's too computationally intensive. And so we have this concept known as gradient descent. And gradient descent is a mathematical concept where you're trying to find the lowest point of a function. The way to think about it is maybe you're at the top of a mountain, we're climbing in Yosemite, and we want to get down to the valley, right? The only problem is we don't actually have a complete view to the bottom of the valley. We see like middle hillocks, and we might be climbing down here, and we might think we've got to the bottom, but we actually haven't. It's all the way down here. But as a close approximation, it's not a bad technique because all you do is as you're walking down your mountain, you just figure out which direction is a slope, and I'm just going to go to the slope, go down to this slope which has which is closest to the direction I want to go to. So I want to just reduce it. And then it's difficult, because you've got lots and lots of layers, lots and lots of weights, it's difficult to actually compute visually in more than dimensions. But like in 3 dimensions, you can look at this, where we're trying to get to the bottom of the curve. We're trying to reduce the error, and that's what we're trying to do. And we're trying to reduce the error with respect to each weight in the system. So how does this work in actual practice? So let's take the handwritten characters, which I worked on like 30 years ago. And this is actually a much simpler problem than what I worked on, which was I was trying to work on cursive characters where the letters were joined up together. And so we've got our labeled data, and we've labeled each character with a number. And there's a data set called MNIST, which has got tens of thousands of characters, and it's got the pixel data for each character. And typically what you do, you split up the data into training and test. So usually you don't train on the entire set because you can get what's called overtraining, because it will recognize things in the training set, but it won't recognize things outside of the training set. So let's take this example here. So each character is 28 by 28 pixels. So if you multiply that out, you've got 784 total pixels. And each pixel is numbered between 0 and 255. So if it's black, it's 255. If it's 0, if it's white, it's 0. Right? So we just label it. And we train a neural net on it. And the outputs, so it could be one neural net, and the output could be 0 to 9. So you've got 10 characters, and we find out the probability of, not the probability, it doesn't always map to probability, the highest score of the final output mapping to the character that's come in. So if you're putting a 5, ideally you want the number 5 to have the highest score. If you put in a 0, you want 0 to have the highest score. Put in a 9, you want 9 to have the highest score. You might have other numbers that are high as well, but you want, the ideal scenario is to collect a 9. So basically in neural nets, you have to collect the data, process the data, build your network. If you choose your architecture for the network, train it, test it, and then go all over again if the accuracy is not correct. So this is like a problem we have. This is a nice little demonstration. It's like a toy kind of implementation. And basically they put up some problems. So we've got orange dots and blue dots, and we need to figure out a classifier. So we're going to build a network doing it. And so they've put inputs. They haven't called it X and Y, but you can call it, they've called it X1 and X2. And they say, oh, you can also put in X squared if you want, or X1 squared, X2 squared. And first of all, we look at the simple problem. This is is this a linear problem or a non-linear problem, first of all? Who can? Linear, right, exactly. So pretty much almost anything works. And you can change, what you can do is you can look at for now, look at the learning rate and the activation. And you can simply just run this, and pretty much almost anything works. And over here on the right-hand side, it tells you the error that you've got here. Okay, great. Okay, so that's a linear problem. Pretty much you're fine. You can try different numbers of neurons and different numbers of inputs, and pretty much almost anything works. Now, if we go to something a bit more complicated, this is a non-linear pattern, right? And in this case, we need more hidden layers to solve this problem. And we can just see what works here. There we go. All right. I should have so has anyone had a go at running that, adding another layer? Yes.
What you said earlier. What is the problem you're solving?
Okay, the problem is trying to separate the orange dots to the blue dots, right? And you've just got X1s and X2. It could be X and Y. Okay, has everyone got that? You got that? Okay, all right. Well, this is easy peasy stuff. So, right, then we've got this one. Now, I think I'll let you guys do this one. And we'll see who's going to have the lowest error. Who's going to have the lowest error? So I want each of you to try and separate the blue dots from the orange dots. Try with more different layers, different numbers of neurons, and see what you come up with.
What are we trying to optimize?
The lowest error. So this is like lesson 1 is working out these architectures. It's a bit of an art. I couldn't give you a recipe, right, on what to use. We'll do one final test, one final example. This is much harder, and see what you come out with. Let's do the spiral one. This is the bottom right. And I think I'll just cold call it. Yeah, over there.
Error is training loss.
Okay, both. Right, let me throw that question out. Which is more important, training loss or test loss?
Test loss.
Why is test loss more important? Who said that? Back there, unseen data. It's much. Who cares? Once you've got the model, test loss is more important because you want it for new data. You want it. That's why we separated it out. Okay, who's got an answer for this one? Have you got one? Oh, I'll start a cold.
So, like my instinct would be to convert this to radial coordinates first.
Yeah, you can do that. Kind of. You can turn it into. Well, actually, first of all, why? Why would you do that?
I don't know. The data looks like it calls for it.
And so a version of that is maybe turn it into signs. Yeah. You could do that. Well, see if that works. What's interesting also the weights. The orange means it says these are negative weights if it's orange, and if it's blue, it's a positive weight. Has anyone got an answer yet? A low error over here.
For the previous one, I got a 0 loss.
That's okay. That means you've got a very good model. Yeah, for the circle one, yeah. I think I got 0 loss for that one too. All right, okay. So this is a sort of a little toy example of you can show your kids how this works, or your friends or colleagues of what's going on. Yes, go ahead.
I'm not able to connect what you presented to what you're doing here. The reason, let's say why I do that. What I understood is the neuron functions kind of constant, right? Number of neurons can change. Ultimately, you're doing weights and additive weights.
Yes.
Multiplied by the thing.
Yes.
And then there's an output function is the same.
Correct. Right. You've understood that. Excellent.
The second and third layer is constant, except that you're changing number of neurons and what feeds into
Right.
the other.
Correct. Yes. Correct.
Now, how do I identify on a given data set? What are these? In this case, it says use sine, use x squared, x.
Right.
How do I-
Okay. Good question. These are the inputs, right? So let's say not sure what this pattern could be. This could be something to do with astronomy or something. It could be the distance of planets from, maybe you've got planets and asteroids. What's the difference, right? Is it a planet or an asteroid? And all you've got is the speed of the planet around the sun, or the asteroid around the sun, the asteroid belt. That's all you've got. And so maybe you've got speed and the direction, maybe speed and direction. So maybe x1 is speed, x2 is direction. And so what the gentleman over there was doing, he's saying, well, we could just put speed and direction, that's it, that's what we've got, and just do that. And by the way, some people do that, just take the data, don't do any feature engineering, don't do any wrangling. But the gentleman over there, what's your name, sir? Ranjit said, oh, well, this is a circular thing, I should turn it into polar coordinates. That means maybe sines, they've got curves, sines are more curved. Maybe it would be easier to do it if I turn the features as sines as well, right? So that's what we call feature engineering. Is that a bit clearer over there?
So it appears that you're using half the data set for the training part.
Right,
And the other half for testing.
correct.
Why not more of the training set be like 67%?
Yeah, that's a perfectly valid, you could use more. And
Would that improve immediately?
well, here's the deal, right? So you've got this trade-off, and often people do 3 sets even, they call it the cross-validation set, so training, a test, and another set that's even separate to the real test set. So if you haven't got much data, you might say use 80-20, but if you use 100, you've got this danger that you create a model that works great on the training set, but it won't work good on the test set. So often, you're talking to your data science, that's a classic question to ask. Now, what data did you train it? And, it's like 101. You mean you didn't actually have a test set, you just trained it on the training set. You have a big danger it won't work in the real world then.
But intuitively, one would expect or want to use more
More data, yes, correct. Yeah, well, the thing is, that is an intuition, but think about it in the back of your head. There's a chance that the real test set, the real test data, may not be reflected. They call this generalization, right? Okay, so there's a test item that I don't have in the training set. I don't have anything that's exactly the same as a test item, but I have something that's close to it, right? And so I can just generalize to that one. And if you put only the whole training set, then you're in danger that you will not generalize to anything else outside of the training set. Over here.
Can you also speak to the noise and batch size?
Yeah, the batch size, those are sort of in a longer class. We can talk more about that, but basically we put data in batches. So we might say, well, let's update the data. No, let's not update the weights every single data item, every single cycle. Just update it every 10 examples instead of one example. And then noise is relating to the perturbing of the data, right? So we haven't got enough data. One way to increase it, just add noise to it so we can have extra data. So these are all little techniques. You can go ahead. Adhar, yes.
So is there like a guideline on what percentage of data should be used for training versus testing? Or it depends on the problem?
No, the guideline usually 50-50. If you want to be really good at it, you should have 3 sets, right? And there's I teach a whole class on this. How to detect overtraining and undertraining. You basically look at the training curve and detect whether it is actually overtraining accordingly. So if your curve is going, where the training curve and the test curve, if they're going too far away from each other, then you know you haven't got, you're not getting enough generalization. So there are some ways you can actually work on this. So I'll stop there. Is that the right timing, Andrew? Okay, exactly on time. Okay, thank you.